Morning. Let's go ahead and get started. Do we have any questions? All right. So usually when there's no questions, it means either everything is very clear or nothing is clear at all. So please give me some feedback. There's no problem, no shame in asking questions. When I was a student, I was very quiet, sitting in the back of the class. Now I regret that. You should really give me a hard time asking questions. And please remember that you may have a question. It may sound silly to you, but 20 other students in class may have the same question. So please ask it so I can explain it to everybody rather than in my office explaining it to 20 different people. All right, so we had the quiz last time. Let's go through the solution. I don't have it graded yet, but let's go through the solution. We had a single phase half-wave rectifier, just an SCR and a resistive load. And the source in this case is a triangular waveform to make it a little bit complicated, for instance. And we have the gate triggering signal also provided, which is basically this signal over here. And what we have been asked to do is, for instance, sketch the waveform of the output voltage. So before any gate signal has arrived, nothing has been going on in the system, so you could expect that your output voltage is 0. All right. Now, I don't know what is going on here. Okay. Then we are triggering the gate. That means the SCR is going to turn on, and it is in the. I don't know why this thing disappears. Let me see. Maybe I messed something up here. Turn it off. Okay. Then we turn the SCR on. The SCR, before being triggered, was in the forward biasing region, meaning that there was some positive voltage appearing across the SCR. So it's ready to be triggered, ready to conduct, and we trigger it. So it's going to conduct. When it is turning on, it behaves like a short circuit, an ideal short circuit. That means basically we are shorting the input voltage to the output voltage, and that means the output voltage is exactly going to follow the input voltage. So such a waveform is going to appear on the output voltage, and then the SCR is going to turn off when the current tends to return back to 0, and that's actually at this time instant, which is 8 seconds. Beyond this point, the SCR is off again. Now, we are also triggering the SCR over here, but this is more like a false triggering because the SCR is reverse bias in this case because the input voltage is negative. Therefore, by triggering the SCR here, nothing really happens. So, from 8 to 16, we got no action going on. SCR is open, basically. It doesn't matter even if you trigger it or not. And then obviously the next cycle starts. So we get something like this. So this is our output voltage. Part B is asking about the waveform of the SCR voltage. Well, if you apply KVL to this loop, you would realize that negative Vn plus VSCR plus Vout is 0, or VSCR is Vn minus Vout. We have both of these waveforms available now, so you can plot it. Over here, the SCR is blocking some positive voltage. It is in the positive blocking region. From 2 to 8, the SCR is on. So it's like a short circuit. And then from 8 to 16, it is off. So whatever the input voltage is appears here. And then this repeats. Something like that. So this is the voltage across your SCR. And part C is asking about find the average value of the output voltage basically what you got to do is find this area over here and then divide that by 1 period, which is 16, and then that will be your average value. So in order to find that area, well, obviously you can write the math, but there is an easy way of doing that. So this is 4, this is 2, this is 10, and this is 5. You can break this down to a trapezoid. You can easily find the area under this trapezoid, and then you can look at this triangle as well. All right, now we have a problem switching colors. What's happening? Okay. And then add them together, divided by 16, and that's the average. I don't have the numerical answer right now, but that's actually what the solution is. Or you could actually find the equation of this line over here, the equation of this line over here, and go with the very basic way of finding the area under a particular curve or a trace, or in this particular case, a line. All right, that was it. Any questions?
So how did you get 5 over there?
Yes, we do get 5 over here because if you look at this triangle, 2 is half of 4, and therefore this number should be half of 10. So, yes, that's 5. Other questions? Okay. So let's move on to our lecture. Last time we kind of wrapped up chapters, I guess 5 and 6. Anything that has something to do with rectifiers, or the brief discussion that we had on AC to AC kind of controllers. And then we started a new chapter which covers DC to DC converters. And the first converter that we started analyzing was the buck converter. Oops. And the circuit diagram looks like this. So we have a switch and a diode. We have an inductor, a capacitor, and a resistor. The resistor is representing our load. It's consuming power. We have a DC source, which is Vs, for instance, here, or Vn in my notes, supplying power. And the rest of the components are the components of your converter. So technically, we have one switch, one diode, one inductor, one capacitor. And that's pretty much it whenever we are talking about classic DC to DC converters. We kind of analyzed this system last time. For instance, when you turn the switch on in the first mode, first of all, the command that you are applying to this switch in terms of being on or being off, which is basically the gate signal that you're applying to the IGBT or the MOSFET that is physically realizing this switch, is a periodic waveform. Usually the assumption is at the beginning of the period, we turn the switch on, then it is on for a specific portion of time, and then for the remaining part of the period, we turn it off. When the switch is on, we discussed it last time, the diode is reversed bias. So the diode is out of the picture. So technically, you have a DC source applied to an RLC circuit. It's a second order circuit. You have to solve it, but the trick that we play over here to avoid solving a second order system is we assume that the output voltage is almost DC and constant. And actually in the simulation that I showed you guys last time, we saw that this really exists. So by making such an assumption, instead of dealing with the dynamics of one inductor and one capacitor, we only have to deal with the dynamic of just one inductor. We eliminate kind of the dynamics of this cap because we are assuming that the voltage of the cap is almost constant. And then when we open up the switch, because the current of the inductor is non-zero and the current of an inductor represents the energy that is stored in the inductor. If you look at the equation, remember when we have an inductor like this, and there is a certain amount of current passing through this inductor, the energy that is stored in this inductor is an expression like this. L is the value of the inductor, I is the current of the inductor. So remember, energy is conserved. 1/2 is constant, L is constant. That means the inductor current should be continuous. We can never ever, under normal circumstances, have the current of an inductor jumping from one value to the other. So if somebody tells you, I was in the lab and I was actually looking at my inductor current and it looked like this, I mean, mathematically you can argue it exists, but practically it doesn't exist, because that means you're jumping from one energy state to the other instantly. That's impossible. So remember, inductor currents are always continuous. You may see something like this in the lab, but you cannot see a sudden jump up or down in the value of the inductor. So this is kind of being useful in the second mode, because in the second mode we have opened up the switch. So previously we had some conduction going on over here. This switch was on and it was conducting the current of the inductor. Then all of a sudden we open up the switch. This current has to be continuous because it's the current of an inductor. So if there is no path here because we have opened up the switch, therefore there should be a path here. That means the inductor forces the diode to conduct in the beginning of the second mode, and that is when we have turned the switch off. Now, let me also talk about another circuit that may be useful for you guys, and that is a system like this. All right. Over here we have a switch that we can turn on and off, and then we have like a physical device. It is not a diode, it is a physical device, and it has like two terminals that are very, very close to each other. So what happens is, when you close the switch over here, the current of the inductor starts from 0 and ramps up, okay, like a DC system. And then when you open up the switch, remember, the energy of this inductor is conserved. You are blocking the conduction in this path, so there should be some current flowing in this path, okay? So that means, and remember, this is more like an open circuit, but these two terminals are very close to each other, like 0.5 millimeter or something like that. So what happens is, you are actually forcing the current to pass through this air over here. So you're going to actually create a spark, okay? And that's actually how you get ignition in an internal combustion engine. So this is a very simple, basic mechanism to generate some ignition. So you can generate some spark, and then the fuel gets, flamed and everything like that. Now in our case, we are almost doing the same thing. Instead of having this component over here, we have a diode. So now when we open up the switch, the inductor forces the diode to conduct. Okay. So mode 1, switch is closed. We looked at mode 1 over here. Switch is closed. The duration of this mode is from the beginning of the period all the way down to D times T. T is the switching period, capital T, and D is the duty cycle, and we define duty cycle as the on time of the switch divided by the entire period. So basically, if this is one entire period over here, this is D times the period. So like 20% of the period, 30% of the period. D doesn't have any units or dimension. All right. We looked at the equations over here. In this mode, what's happening is, assuming that the output voltage is constant and positive, we are applying a positive voltage across the terminals of the inductor. Therefore, the current of the inductor is kind of integrating this voltage to give us the current, and the current looks like this. All right? So the current rises from some minimum initial value to a maximum value. And we wrote a bunch of equations. For instance, equation number 1 describes the equation for this line. Equation number 2 describes what is the ultimate or maximum value of the current in this mode. And also delta IL in red is how much the inductor current actually rose in this mode. Then we looked at mode number 2, switch turns off. Well, obviously this is happening during the remaining of the period. So from dt all the way to the end of the period, which is t, and diode turns on because the inductor current is continuous, and the inductor current is non-zero and continuous. And what's happening is you're kind of applying kind of like a short circuit across this across the diode, basically. So let me erase this. All right, and this one. Okay, just a little bit more here. Okay, so if you look at the voltage that appears across the inductor in this case, it's just the negative of the output voltage. If the output voltage is positive, and later on we have to check if it is really positive or not, it is actually, but we have to double check in the end. That means we are applying a negative voltage across the inductor. That means the current of the inductor is going to fall. So if you're interested in drawing the inductor current in this mode, the current initially was at a maximum value, which was determined from the previous mode, and now we are applying a negative voltage, a negative constant voltage across the inductor, so it just falls down, okay? And the equation for this would be, in this mode, it starts from a maximum value, ramps down, therefore we have a negative slope over here. Something like this. Okay, the slope is negative, which is negative V out over L, and that is the voltage appearing across the inductor over the value of the inductor. That's always the slope times time, and time starts at dt, so there's a little bit of a time shift here as well. All right. So now we kind of have looked at what happens in the system when the switch is on in the first mode, and what happens in the system when the switch is off and the diode is on in the second mode. So now we can actually look at these and, for instance, find the voltage transfer ratio. Okay. So in order to find the voltage transfer ratio, we are assuming that we are analyzing the system under steady state conditions. So, okay. When I say steady state, that means on average nothing is growing or shrinking or reducing, basically, okay? So for instance, on average, the voltage drop across the inductor, on average, the current of the inductor is constant. Or on average, the voltage drop across the inductor should be zero. These are all indications of a steady state condition. Or on average, the voltage across the cap is constant. Or on average, the current that is passing through the cap is zero. So these are all indications of steady state. It means on average, nothing is growing or going down. So on average, the inductor current is kind of hovering around some constant value, something like that. So this is an indication of a steady state. All right. So if this is a steady state, that means one of the conclusions that you can get is, on average, the voltage drop across the inductor should be zero, because on average the current of the inductor is neither increasing or decreasing. Okay, so let's see. In mode 1, I had VL was Vn minus V out. Okay, this is the equation that we had earlier up here, over here. All right, VL was Vn minus V out. In mode 2, I had VL was negative V out. Okay? And this is what we had over here. All right? So on average, I should make sure this is 0. And by the way, we should, when we are trying to get the average of this thing, we have to look at how long they are. So this was from 0 to dt. This was from dt to t. Okay? So I would say the value of the voltage drop across the inductor in the first mode times the duration of the first mode plus the value of the voltage across the inductor in the second mode times the duration of the second mode should be 0. Okay, so if you manipulate this equation, you are going to end up with V out over V in equals D. So this is our voltage transfer ratio. Okay, it indicates that if you have this buck converter under ideal circumstances, V out is just the value that we choose for the duty cycle times the value of the input voltage. It is independent of the load resistance. It is independent of the value of the cap that you're using, as long as you are in that time frame, in that frame of operation. And it is independent of, for instance, the switching frequency. It is independent on the value of the inductor you have chosen. So this is a very, very simple equation. Describes the voltage transfer ratio of the buck converter. So this is for buck. All right. If you remember how we define the duty cycle, it is always between 0 and 1, indicating that the output voltage is always less than the input voltage and positive. All right. So this is the place that you have to go and check. For instance, here when I was drawing this line over here, I assumed that V out was positive, therefore negative V out was negative. And this is actually an indication, yes, V out is positive. Or when I was plotting this line over here, I assumed that the slope was positive, or Vn minus V out is positive, or Vn is greater than V out. And if you look over here, you can see that, yeah, you can confirm that Vn is greater than V out. So any assumption that you make, in the end, you have to go and check and make sure that assumption was a valid assumption. There are other ways of finding this equation over here. And for instance, one other way that you can see in my notes and also appears in the book is we found delta IL in the first mode. All right? Over here, we found delta IL, how much the inductor current rises. We can also find delta IL in this mode. And then compare them, basically, okay? So in this case, delta IL would be, which is, okay. So if I call this I min again, the assumption is we are operating under steady state conditions, meaning that the initial value of the inductor current, which was I min at time equals to 0, is the same as the final value of the inductor current at time equals t. Okay, so that's why I did not label these two values differently. I just said, okay, initial value is I min, final value is also I min. Why? Because we are operating under steady state conditions. That means IL at t equal to 0 is the same as IL at t equals to t. All right? So this is another indication of operating under steady state conditions. So inductor current returns back to where it started from. Okay, something like that. All right. So if you look at delta I over here, which is again I max minus I min. Now a lot of students get confused over here. They write I min minus I max. So please remember delta IL is the amount of rise. It's always the larger value minus the smaller value. This would be the slope in a positive way, which is V out over L, times the duration, which is 1 minus D times T. All right? All right. So this is delta IL in the second mode. So I have one description for delta IL over here. I have another delta IL description over here. They should be the same, okay? So let me see if I've labeled my equations. Okay. So this delta IL over here, let me just mark it with a star, should be the same as this delta IL over here. Let me mark it with 2 stars. Okay. So let me write it down here. If I compare a star with double star, the delta IL in the first mode is supposed to be it's similar to the delta IL in the second mode. Okay, in the first mode we had Vn minus V out over L times D times T should be the same as V out over L times 1 minus D times T. Again, bunch of parameters cancel out, and again you will end up having this equation of V out over Vn is D. Okay. So as long as you have a buck converter, this is your voltage transfer ratio. Now please remember, we have made a bunch of assumptions to get to this voltage transfer ratio. For instance, one assumption was that our components are ideal. The switch and the diode that I have are ideal components. The other assumption is the converter is operating under steady state conditions, and I use that actually condition. That means the final value of the inductor current and the initial value of the inductor current are the same, or on average, the voltage drop across the inductor is 0. The other one is the converter is operating at continuous conduction mode. Now, what does that mean? Continuous conduction mode means IL is always positive. It never touches the 0 level. Don't worry about it for now, but later on we are going to actually analyze converters that are not operating under steady state conditions, and you are going to realize that the voltage transfer ratio is going to be different. So I'm going to make a note over here. Buck if CCM. Okay, CCM stands for continuous conduction mode, meaning that IL at any given time is positive. It never touches 0. It's always it's above 0 at any given time. All right. The other assumption that I made, which simplified a second order system to a first order system, was the output voltage was very large. So keep that in mind as well. The output capacitor is very large. I'm sorry. That means the output voltage is almost constant. And the other assumption that we make is that the switching transients are instant, meaning that as soon as I turn the switch closed, the diode is off, or as soon as I open up the switch, the diode is on. So there is, in a real case, there is a little bit of a transient going on from switch turning off to diode turning on. But over here, we are just assuming that everything is just instantly happening. All right. So keep these conditions in mind, and we are going to review these conditions again when we get to any kind of converter like boost, buck boost, things like that. So please remember, always you have to question yourself, do these conditions actually hold? Now, we looked at the average value of the inductor current over here and made sure this is supposed to be 0, but you can also plot a bunch of waveforms actually. Let me see if I need to plot them. Yeah, actually I have them here. Let me just use what I have already in the notes. So these are the waveforms. Okay. So you look at on the top trace, first of all, you always start with what's happening to the switch, what kind of command is applied to your switch. So I'm assuming that this is one period, and I am keeping the switch on in this portion of the period, which is duty cycle times period, and then the switch is off. All right? When the switch is on, Vx is basically this voltage over here. The voltage across the diode in a reverse manner, basically assuming that this is my ground, Vx is actually measuring the voltage of the left-hand side terminal of the inductor with respect to the ground. So Obviously, when the switch is on, Vx and Vn are the same. When the switch is off, the diode is on, and therefore Vx is 0. So Vx, whenever the switch is on, Vx and Vn are the same. Whenever the switch is off, Vx is 0. All right? And we also argued about VL. VL in the first mode was Vn minus Vout. So this is Vn minus Vout. In the second mode, it was negative Vout. And on average, it should be 0, meaning that this positive area should be the same as this negative area. And that's how we found the voltage transfer ratio. And finally, the inductor current. In the first mode, VL is positive. You're applying a constant positive voltage across an inductor. Therefore, it just linearly ramps up. In the second mode, we are applying negative Vout on the inductor, so it actually falls down again linearly, and it's a periodic waveform. Initial value and final values are the same. We label this value, which is the same as this value, to be I min, and we label this value, which is the same as this, to be I max. So things are periodically repeating themselves, and actually we saw that in the simulation as well. So these are some of the waveforms, and sometimes in a quiz you are asked, for instance, to draw some of these waveforms. What is the voltage drop across the diode? What is the voltage drop across the inductor? What is the current waveform of a diode? Let's actually look at the current waveform of the switch and the current waveform of the diode. Let me draw them here, for instance. Let's say we are interested in the current waveform of the switch, IS. By S I mean switch, not the source. So this is what I mean by IS. And later on ID. All right? So obviously when the switch is on, the diode is off, the current of the switch, and that's happening in the first mode. The current of the switch and the current of the inductor are the same. In the second mode, the switch is off, so therefore it's not conducting any current, therefore the current is 0. So second mode is very, very easy. It's 0. In the first mode, it is actually following the inductor current waveform. So this is your switch current, which turns out to be the same as your input current, basically. So switch current and input current in the buck converter are the same. And obviously this is I max, and this is I min. All right? And this is a periodic thing, so this is also happening here. And here. And so on and so forth. So this is the way your input current looks like. And this is considered one of the disadvantages of the buck converter. Your input current, or the current that you're drawing from the source, is not continuous. It's a bad thing, actually. There's going to be some noise, and if your source has some internal resistance, the voltage of the source is going to change, and it's going to have a negative impact on other components if they are also connected to your source. But we don't want to get into the details of that. Also, let's look at the current waveform of the diode. Remember, the current of a diode is always assumed to flow from anode to cathode, and it is always supposed to be positive or 0. It cannot be negative. In the first mode, the switch was on and the diode was off, so there is no current. In the second mode, the diode was conducting the current of the inductor. So whatever current inductor I have over here, I have to plot it over here. So this peak is I max. This minimum value is I min. And this is T, and this is dt. Okay, and you can see how it looks like. So this is the current waveform of the diode, and as we expected, it is always either 0 or positive. It's never negative. All right, pretty much all the current waveforms that we want to know are here, except, for instance, later we want to, for instance, look at the current of the cap and those kind of things. All right, so let's actually talk about that a little bit. All right, one actually argument that you can make is, and by the way, when I was dealing with I, S, and ID, if you apply KCL at this node, you would argue that IS plus ID, current of the switch, plus current of the diode, should be IL, which is the current of the inductor. And that's actually what you have here. If I add these two blue traces with each other, I should be able to get IL, and I do actually. So please remember, in the Bach converter, IS plus ID is the same as IL. Okay, so when you add up, if you want to double check your solution, if you add up these two traces with each other, you should be able to reconstruct IL. All right. All right. So let's talk about the capacitor. Actually, we have some arguments over here. We start with the fact that the current of the inductor is the current of the cap plus the current of the load. Okay. The current of the inductor, I'm applying KCL over here. The current of the inductor is the current of the cap plus the current of the load, IR plus IC at any given time. And this is actually this equation over here. At any given time, KCL mandates that the inductor current is the same as the cap current plus the load current. All right, if this holds at any given time, I should be able to get the average value of both sides, and again, this equation should hold. So now I'm looking at the average value of these signals, and now they should be the same. Average value of the inductor current is the same as the average value of the cap current plus the average value of the load current. All right. So please remember, we assume that we are operating or we are analyzing the system under steady state conditions, meaning that the cap current on average is 0. So another indication of a steady state operation is, let me write it over here where we had a steady state. So another indication of a steady state operation means on average the current of the cap is 0, or if you look at the voltage of the cap at the beginning of the cycle and then look at it at the end of the cycle, they should be the same. All right, meaning that on average the voltage of the cap is neither rising or falling, or on average there is no current going into or out of the cap. Okay, so remember, on average the cap is neither getting charged nor discharged. It's just maintaining an almost constant voltage. All right, so pretty much I can argue, I just made the argument that this is 0. On average, the capacitor is neither getting charged nor discharged. Now, what is the average value of the load current? Because my load is just a purely resistive load, the average value of the load current is the average value of the output current over R. Okay? Now, what is the average value of the output current? I just assume my output is almost DC. It doesn't even have any ripple. So actually, instead of V out with lower cases, meaning that it's a function of time, I can say this is almost the same as whatever DC value I have for my output voltage over R. Okay? So let me plug these all in. So if you do that, your equation is going to end up with this equation over here. So on average, IL is 0, which is the average value of the cap current, plus V out over R. And that's the equation that I have over here. All right, which is the equation, which this equation is labeled to be number 6. So the average value of the inductor current is the same as my load current. This is very, very important. A lot of people get this confused. So if I focus my inductor current, focus at my inductor current, which is like this trace over here. So this is IL. And then find the average value of this trace, and it's a very symmetric triangular waveform. The average value is quite easy to find, and let's say I've already done that, and it's like this. Okay, so this is my load current. So if the inductor current is provided to you, all you have to do is just take the average value, which turns out to be actually I max plus I min over 2, the average value between I max and I min, and because it's a symmetric triangular waveform, that's your load current. And there is an equation here for it as well. So my load current, or the average value of the load current, capital I of R being the resistive load, is I max plus I min over 2, because this is a triangular kind of a symmetric waveform. So the average, in order to find the average value of the signal, I just have to get the average value of its maximum value and its minimum values. All right. So I have the average value, I have the load current. Now I can go back and find the current that goes through the cap. Going to that initial KCL that I had, inductor current minus load current is the cap current, right? So I have the inductor current, which is the blue trace. I have the load current, or at least, remember, load current and the average value of the load current are almost the same. So if I subtract these two waveforms from each other, I can find the capacitor current, and that's actually the waveform that we have over here. So this is the inductor current minus its own average. Or technically what you do is you kind of, you know, this red dotted line that I have over here, which is the load current, I just drag this thing down to align with 0. So that means this whole waveform over here has to go down to the 0 level, and that's actually your capacitor current. All right. So as you can see, the cap current on average is 0, and it doesn't violate our initial steady state assumption, because remember we made the assumption of under steady state conditions the average value of the cap should be 0. All right, over here, and you can see it holds. On average, I have a triangular waveform, but on average the value of this thing is 0, meaning that this positive area cancels out this negative area. Okay, so that's one conclusion, and we're going to use this to actually find the right value, for instance, for our capacitor when we are trying to design the system. All right, a bunch of other equations are written over here. One of them is, I just talked about it, the average value of the load current. So IR, so let me write it up here. IR is almost the same as the instantaneous value of the current of the load. And obviously these are all load currents. Okay, load currents. Load current. This one is the average value of the load current, and the right one is the instantaneous value of the load current, and they're almost the same. Why? Because I assume that my output capacitor is large, my output voltage is almost DC, there's almost no ripple on it, therefore you can't really identify between the average value of the signal and the instantaneous value of the signal. And the same argument holds for the current, because it's just a purely resistive thing. So this equation over here comes from, looking at these blue curve and trying to find the average value. It's very easy. It's a triangular waveform. This equation over here comes from the fact that, let me rewrite over here a little bit larger. This is I max. This is I min. And this is IL. Okay? I also argue that the average value of this thing is IR, which is the load current. And previously we had labeled this to be delta IL. Okay? Which is the changes in the inductor current in one of our modes, either mode 1 or 2. Because again everything is symmetric, you can argue that this is delta IL over 2 and this part is also delta IL over 2. Alright? Alright? Now, so you can actually write it in this way. You can say, okay, I max is the load current, which is that red line, plus delta IL over 2. All right? Or I min is the load current minus delta IL over 2. Okay? And we may need these equations later. Okay? Now, sometimes you have a problem. You have to find the maximum value of the inductor current, the minimum value of the inductor current, and these equations come in handy. So let me rewrite them in terms of the parameters that we have. For instance, I max is IR, which is the load current, which is V out over R in DC terms, plus for delta IL we had two descriptions. One of them was obtained from mode 1, the other one was obtained from mode 2. It's up to you, whichever you want to use. Over here, I don't know which one I'm using honestly, so it's V out times 1 minus D, V out over L. Let me see which one we are using. I guess we are using this one. All right, this is my delta IL. All I have to do is divide it by 2. Instead of T, which is the switching period, it's easier to talk about the switching frequency, so which is 1 over F, and that's it. So let me just rewrite it over here. V out over L times 1 minus D. There is a division by 2 involved because this is delta IL over 2, and there is division by F involved because previously we were multiplying that by the switching period, or you can even write it in this form. Two times the value of the inductor times the frequency. So these equations come in handy when there's a problem. You have to find the maximum value of the current or the minimum value of the current. And this one is labeled to be equation number 8. And you can do the same thing for I min, which is equation number 7, and I min will be almost the same thing with a negative sign in it. 1 over R minus 1 minus D over 2LF. And this would be equation number 7. And please remember, F, which is the switching period, is 1 over, F, which is the switching frequency, is the 1 over T, which is the switching period. So these are the same equations that I have over here in terms of Imin and Imax. Okay? And again, reminder, we are assuming that we are analyzing this system under a continuous conduction mode, or abbreviated as CCM, meaning that the minimum value of the inductor current is positive. If you're doing the math and realize Imin is either 0 or negative, that means you have to, a question mark should be raised in your mind that what is going on? How come Imin is not positive? Either you have made a mistake in calculating Imin, or your original or initial assumption of operating under CCM was not a correct assumption. So please remember, best way to check if you are in CCM or DCM is looking at this equation over here. This tells us if CCM holds or not. All right? So if you have a problem, you're trying to find out, are we in CCM or not in CCM, you have to find Imin. If it is negative, then you are not in CCM, basically. All right. At the same time, this equation gives us some guidelines on how to design or find an appropriate value or appropriate size for the inductor. So I'm saying that, let me rewrite this. This is actually kind of chopped off. So let's say I would like my system to operate under CCM conditions, which kind of mandates for Imin to be positive. All right? So I have a description for Imin. So let's write it and see under what conditions this should be positive, or this turns out to be positive. All right. So in other words, V out times 1 over R minus 1 minus D over 2 times L times F should be positive. All right. V out is positive. You can just get rid of it. And technically, you can argue that as long as L is greater than twice the frequency, we are in good shape. So if somebody asks you, okay, I have these parameters for my converter and we would like to use this converter to operate under CCM, what is the right size for the inductor? You should be using this equation. This is a very, very, very important equation when it comes to designing the system. It doesn't give you what the exact value of L should be, it just gives you a boundary of L should be larger than this expression. And for that reason, there is a critical value in the book. It's actually called the critical value, L critical. All right. So if you choose L to be exactly equal to the L critical, that means you are at the boundary of CCM and DCM. So technically, your inductor current looks like this. It starts at 0, goes up, comes down to 0, never goes to negative values, but it is just touching the 0 level. IL at boundary. Oops. I'm not sure how boundaries is spelled. I'm assuming it's with an A. Boundary condition. Okay? So this is the critical value for the inductor. But usually we want to go a little bit beyond this to make sure we are deep in the continuous conduction mode region. Now, when you are using this equation, you should actually consider several things. One of them is F, which is the switching frequency, is constant, so don't worry about it. But R, your load, might be variable. So if you're dealing with a variable load case, what you got to do is you got to maximize this expression under the conditions provided to you, and then make sure L is even larger than the maximum possible, okay? So if your load is a variable load, you should consider the maximum value of the load to maximize the expression. Also, sometimes your duty cycle is variable. For instance, your input voltage is variable. For that reason, your duty cycle is variable. And you want to maximize this expression. We have 1 minus d. In order to maximize 1 minus d, I have to use a minimum value for the duty cycle. Okay? So very simple. And a lot of students make mistake. They use the wrong value for the range that has been provided. So if your load has a range of minimum to maximum value, and your duty cycle has a range of minimum to maximum values, for the duty cycle, you should use the minimum value. For the load, you should use the maximum value. All right. All right, so this is a very, very important equation to find or design the value of L. I'm going to write this equation number 9, label it number 9. And so one thing that I also want to mention is, if you increase the switching frequency, there's a division by switching frequency appearing here, meaning that if you increase the switching frequency, you will need a smaller inductor, okay? And that could be a good thing or a bad thing. Smaller inductors are good because inductors are like the bulkiest components in the system. So if you manage to have a 10 microhenry inductor compared to a 100 microhenry inductor, that's better. The 10 is better than 100 because it's smaller. So in terms of weight and volume, you're saving stuff. You know, for instance, you're sending a shuttle to the space, and weight is very critical to you, and therefore the size of your inductor is very critical to you. So from one end, increasing the switching frequency is good. On the other end, it is not a very great idea, because as you increase the switching frequency, there is a mechanism which is called the switching losses. Your switching losses are going to increase. All right? That means you are making the inductor smaller, but the losses in the system is getting larger. Therefore, you have to use a larger heatsink. So there's a trade-off over here involved. Typically, your switching frequency is 100 kilohertz, okay? So you can actually use that switching frequency to design your inductor. If you want to have a very fancy, like a portable application kind of a thing, for instance, you're designing a buck converter for an iPhone. It has to be embedded, integrated in your iPhone. You may choose a switching frequency of 1 megahertz. Or you are looking at a stationary application and you want to avoid high switching losses, you may choose a switching frequency of maybe 50 kilohertz, maybe 20 kilohertz. Generally speaking, we tend to choose a switching frequency that is larger than 30 kilohertz because our ears can hear up to 30 kilohertz. So if you set your switching frequency beyond that, you cannot hear the buzzing noise of your converter, okay? If it is less than 30 kilohertz, you may be able to hear some buzzing noise coming out of your converter. So that's one boundary. The other thing that is limiting your switching frequency is the kind of switches that they are using. Some switches are faster. For instance, MOSFETs are faster. They can handle higher switching frequencies. Some switches are not as fast. For instance, high-power IGBTs are not very fast. So maybe 100 kilohertz is too much for them. You should run them at 30 kilohertz, maybe 20 kilohertz, sometimes even 10 kilohertz. So switching frequency determines the switching losses, determines the size of the inductor, and later on the size of the cap in the system. And at the same time, it also determines what kind of switches you should use. So if your switching frequency is, for instance, 1 megahertz, there's absolutely no IGBT that can handle that switching frequency. It should be slower than that. All right, so this was about designing the L. And then we have to also talk about designing the cap, the capacitor. In order to do so, we look at the current of the cap. Okay, earlier up here, on this red trace down here, we talked about how the capacitor current looks like. It's a triangular waveform. On average, it is 0. Its peak value in the positive territory is I max minus IR. And we know how to find IR, which is V out over R. We know how to find I max, which is equation number 8 over here. And on the minimum side, it's like I min minus IR. Again, we have an expression to find I min based on the parameters in the system, and also IR, which is the load current, which is just V out over R. So we know in nature what this current waveform looks like. What's the nature of this current waveform? I'm just redrawn this over here. So this is my capacitor current waveform, I of C, I of cap, and I'm trying to find the peak-to-peak ripple of the cap voltage. So far we were assuming that the cap was very large. There was no ripple on it. Everything was pretty much DC, but now actually we are kind of violating ourselves. We are assuming that, oh, there's a little bit of a ripple over there, and I want to find an expression for that ripple. So there is an approximation involved over here, but it is a very, very accurate approximation. So if I have the current of a cap, all I have to do is just integrate that and then divide it by the value of the cap, then add it with the initial value of the cap to find an expression for the voltage of the cap. If you do so, you will end up a curve like this. Please remember the current of the cap was a first order kind of a thing. It's just a linear thing. So the voltage of the cap is going to be in the quadratic form, and that's why we have kind of these curves. For instance, here here you can see that the voltage of the cap is crossing its average value, so you will expect this current is hitting a maximum value or something. I mean, you can actually do, you know, some comparison over here. So our objective over here is find this peak-to-peak ripple of the voltage of the capacitor, which also it is our output voltage. All right. So all we have to do is integrate our capacitor current. Okay, let's talk about this. My cap current is crossing 0 over here. That means my cap voltage is at its minimum value. Again, over here, my cap current is passing 0 again from positive to negative. That means my cap voltage is at its maximum value. Okay. So all I have to do is just sweep the capacitor current from one zero crossing to the other, because that covers pretty much capacitor voltage from one minimum value to the maximum value. So all I have to do is find this little area over here, and that is proportional with the capacitor changes in the cap voltage. So let me actually write it over here because that's a little messy. Okay. So first of all, from physics, we know that Q, which is the electric charge stored in a cap, equals C, which is the value of the cap, times the voltage of the cap. Or changes in the electric charge is the cap value times changes in the voltage of the cap. All right, so we know this from physics. All right, so all I have to do is I focus on one particular area that my cap voltage goes from, for instance, its minimum value to its maximum value, and then see how much electric charge is going into the cap. Remember, electric charge is, again from physics, electric current is the derivation of electric charge with respect to time, or electric charge is kind of the integration of current. All right? So if I have the current waveform, if I find some area over there, that's actually representing my delta Q. So this area over here, let me just highlight it over here because I've already highlighted before. So this is delta Q. If I find this delta Q, that is proportional with changes in my cap voltage, and this is in terms of time is happening from VC minimum to VC maximum, or it is identifying delta V out. Okay? So in that area that I just highlighted, delta Q would be, we are looking at the triangle, basically the base of that triangle multiplied by half of its height. So half of the base, everything is symmetric, so the base of this triangle is T over 2. Okay, this is T over 2, and this is also T over 2 because everything is symmetric. And the height is delta L over 2. All right, so remember when we were looking at the current of the cap, from here to here is delta IL over 2. Because the entire thing is delta IL, then we are looking at half of it, so this is delta IL over 2. So it's very, very easy to find this area, basically. So this is T over 2, and the height is delta IL over 2, and we have expressions for all of them. So that's your delta Q. All right? And remember that delta Q is C times delta V out. Okay? So if you write all these expressions, you will end up with C equals to V out. So for instance, instead of T, I would place 1 over F, which is the frequency. Instead of delta IL, you can use either of these expressions. In this case, actually, I'm using this expression over here. V out over L times Y minus D over T, because I only want to have everything in terms of V out. Because if I use this other delta IL, we have V in here as well. I don't want anything to be described in terms of V in. That's why I'm using the second delta IL that we have. All right, so this is going to be V out over delta V out times 1 minus the duty cycle times 8 times L times F squared. All right, or if you write it in other words, you can argue that the delta V out, which is the peak-to-peak ripple of the output voltage, divided by the DC value of the of V out. And remember, this is a very small thing because the peak-to-peak is very small, equals 1 over D times 8 LCF squared. All right? So these two equations are important when it comes to designing the cap. So the customer says, my V out is supposed to be 5 volts. Then you first go ahead and, for instance, choose a switching frequency of, for instance, 100 kilohertz. Then you use this expression over here to select a value for your inductor, which is also needed here. And then you know what your input voltage is, so you know what your duty cycle is. And then once you have all of this, the customer says, my delta V out should be, for instance, 10 millivolts out of 5 volts. So you have, for instance, V out of 5 volts, delta V out of 5 millivolts, and then you pretty much have everything, so you can easily find your cap. And usually you better go with something just a little bit larger to guarantee that your peak-to-peak ripple is bounded within those requirements. Again, when it comes to a system that, for instance, well, in your system frequency is fixed, L value is fixed, V out is usually fixed, but duty cycle may not be fixed. So remember, you have to maximize this expression. So use a minimum value for your duty cycle so that 1 minus D is maximized. So this whole thing is maximized, and then make sure C is even larger than the maximum. All right. So these are the expressions to choose for cap. And again, I discussed this earlier. If you increase the frequency, then the L that you need is going to get smaller, and also the C that you need is going to get smaller. Okay, so the size of the converter is going to shrink. All right. One last thing before we get to a numerical example, and that is the fact that this is an ideal converter, therefore input power is the same as the output power. Okay? So there is no losses in my system. Whatever power my source is delivering is being delivered to the load. There is no losses in my switch. There is no losses in my inductor. Everything is ideal. So the input power is the same as the output power. What is the input power? A lot of people get confused over here. The input power, remember, we are talking about power that is drawn from a DC source. When you have a DC source, your power is the value of that DC source times the average value of the current that is drawn from that DC source. So that is my Vn times the average value of the input current. All right. What about the output power? Output power is, again, we are talking about a resistor on the output side, which is almost a DC kind of a thing. We are neglecting the ripple again. So that would be DC value of the output voltage times the DC value of the output current, and they're almost DC anyway. So you can see that if you kind of manipulate this equation, you will end up V out over Vn is the average value of input over the input current times the average value of output current divided by the average value of output current. And this was D initially because we said V out over Vn is D for this converter. So sometimes you already know this part, and it comes in handy to assume that, to also use this equation. So on average, the input current divided by load current is also the duty cycle. So think of it like more like a transformer look, you know. V primary over V secondary is I secondary over V primary equals to N2 over N1 or something like that. Over here, like N, the turns ratio of a transformer, is like a D, your duty cycle. And we have already over here, I actually drew the, for instance, waveform of the input current over here. So either you have it, you can find its average value, or you don't have it, but for instance, you have the value of the duty cycle and you have the value of the load current, so you don't have to spend a lot of time find the average value of your input current. You can just use this equation and find it. So this traced over here as my input current is what I drew earlier as my switch current. So remember, they are the same. And again, here I'm drawing the diode current, which I've already drawn earlier. All right. Do we have any questions so far? So things might be a little new. Please read this buck converter very carefully, because we are going to repeat this for the boost converter, for the buck boost converter, for the flyback converter. All these converters have the same principles of analyzing them. So if you are very good at one, you will be good at the other ones as well. All right. Now let's get to a numerical example, how we can use these equations. This example originally comes from the book, and the book suggested that the switching frequency to be chosen at 20 kilohertz, which is relatively old, relatively small. In most older power electronic books, like the books that were published back in the 80s and 90s, they were conservative. The switches were not fast. Switching frequencies were around 20 kilohertz, 30 kilohertz, 50 kilohertz. But now you can easily buy a switch that is fast enough and achieve 100 kilohertz. So the numbers that you see over here are based on the assumption that my switching frequency is 20 kilohertz. And I'm going to actually write it over here. What if my switching frequency is 100 kilohertz? So so let me rewrite it over here. Let me make this a little tinier. Maybe just even further tinier. So we are looking at a buck converter, and the input voltage is 50 volts. The inductor current has already chosen for us, we don't have to choose it, 400 micro. And the cap has already been chosen for us to be 100 microfarad, and the load resistance is 20 ohms. Okay, so this is like somebody has already designed this converter for us, and but they have some questions for us. And by the way, the switching frequency is 100 kilohertz. So the questions that they have is, under two different conditions, for instance, one time we choose the duty cycle to be 40%, and the other time we choose it to be 80%. Okay, so this is like case 1, and this is case 2. Under these two separate cases, For instance, what would be the output voltage? Okay? So, what you got to do is, right now, pretty much it is well designed and CCM holds. So if CCM holds, okay, remember CCM was continuous conduction mode, and all of the equations that we have had so far are valid only, and please pay attention. All of these equations are valid as long as you are operating under CCM. If the CCM is violated, then you should use this different set of equations. Okay, we're running out of time. So I'm going to continue this example, and next time, and then after this example, there is a design example of how to find L and C. And then once we are done with these, we are going to get into the next converter, which is our boost converter. All right, see you guys next week.